Hi everyone. So in this video, we're going to be talking about some different properties of integrals, basically how you can kind of add together different integrals, subtract them, multiply them by different numbers, things like that. Just to kind of remind you, we still haven't learned exactly how to compute the exact value of an integral. So for now, we're still either approximating using rectangles, or there are some situations where we can actually evaluate the integral, right? Just using geometry formulas. So if we have an integral where the function has a shape that gives you like a triangle or a rectangle or a circle or semicircle, those are the types of integrals that we can evaluate at this point. So in the next video, for next week, that's when we will get into actually evaluating integrals. So don't worry, that will come soon enough. Okay, so these properties, they're really important. These are all things that will come up basically throughout the quarter. The first one is that if you're taking the integral from a to b of any function, that is going to be the opposite, so the negative of if you reverse the bounds. So if instead of going from a to b, you go from b to a. And basically the way I would think about it is that, the most typical way of writing down an integral would be to have the smaller bound first and then the bigger bound, right? So for example, one example that we saw in earlier videos was that the integral from 0 to 3 of x squared dx was equal to 9. And again, that's not one that we actually were able to calculate just yet, but basically if you remember, we used different numbers of rectangles and we figured out that the more rectangles we use, the closer the value is getting to 9. And so we kind of guessed that the value is 9, and it turns out is actually the correct value. So notice that when I write this integral down, it's saying the integral from 0 to 3. So the number on the left is this, or on the bottom is the smaller number, because we're talking about an area that's between 0 and 3. But in some circumstances, and we'll see this show up later in the quarter, you might end up with an integral that looks like this instead, the integral from 3 to 0 of x squared dx. And so that doesn't really make sense in terms of the area interpretation, right? Because we should be kind of going from left to right and saying, okay, between here and here. And so the way that we interpret this, if we have the bounds reversed so that the bigger number is on the bottom, we just flip the sign. So this integral would be equal to -9 instead of +9. And there isn't really I wouldn't think of this too much as kind of like a logical interpretation. It's more just a rule, I would say. It's like a definition. So it's defined that if you have your integral in this kind of backwards order, that you just flip the sign from what it would be if it was in the more standard order. Okay, so that's the first one. Second one says that if you're taking the integral from a to a, so from a number to itself of a function, that integral is always going to be equal to 0. So why is that? Well, basically, if your two bounds are the same, going back to this kind of area interpretation of an integral, if you're taking, if you have, let's say, a function that looks like this, and you're doing the integral from a to a, well, there's just no area there, right? There's nothing, if you had another point b over here, then you could talk about an area. But if you bring this other value b, so that's on top of a, there's just no area there. And so that's why we say that the value of that integral is equal to 0. Okay, next up we have if you're taking the integral of a constant. So we've actually seen some examples like this already. So if you're taking the integral of a function that is just a constant function, it's always going to work out that the value of the integral is going to be the value of your constant function times the difference in your bounds. So why is that? It's basically just because if you have a constant function, your your area is just the area of a rectangle. So for example, let's say that you have you're trying to take the integral from 1 to 4 of the function 5. So f of x is equal to 5 looks like just a line at a height of 5. And if you're taking the integral from 1 to 4, well, you're just going to have a rectangle where the base of that rectangle is 4 minus 1, which is 3, and the height of the rectangle is 5. So the area would be 5 times 4 minus 1, which is 5 times 3, which is 15. So I wouldn't really think of this as like a special rule that you have to memorize. It's more just kind of a nice observation that if you're dealing with the integral of a constant, you don't really have to do any work. It's really just thinking about, oh, okay, I just have a rectangle. I know what the base is. I know what the height is based on the bounds of my integral and also the function. And I guess actually that reminds me of something that I don't know if I ever explicitly said this yet. When we're talking about these numbers here, so like these numbers, whatever numbers you're putting as the first and second number on your integral, those are called the bounds of the integral. So I think I probably forgot to actually define that word, but we'll be using that word a lot. So the bounds of the integral just mean what are those two numbers that you're looking at the area between. Okay, so next rule. Let me scroll up. Sorry, my screen's a little stuck. There we go. So this next rule, I have kind of a picture to help illustrate it. So that's what's going on down there. But this rule says that if you're taking the integral from a to b of a sum of two functions, so I'll write that as f of x plus g of x. Rather than take the integral of the whole quantity, you can actually split it up and take the integral of the first function, and then to that add the integral of the second function. And this is going to be a really important rule. We're going to use this idea actually quite a bit in this class. And it also works with subtraction. So I could change this. I'm just going to write plus or minus. So, if you're adding the two functions, you add them. If you're subtracting them, you subtract them. So why does this make sense? I want to kind of argue to you why it makes sense using like the definition of the integral. So remember the integral, we talked about this in the previous video. It comes from this limit of adding up a bunch of rectangles. So for example, let's say that we have two functions. So this function here is f of x, and this function here is g of x. Let's put it up top. So how do you get a function f of x plus g of x? Well, you literally just add together the points on each function, right? So here, if we look at what's happening at x is 0, we have f of 0 is 1, right? We have a point here at 0, 1. And then if we look at g of x, we have 0, 5. And so that means that their sum, f plus g of x, or f of x plus g of x, is going to have a point at a height of 6, because 5 plus 1 is 6. So this purple function, and I did this in Desmos, so this is actually accurate, this purple function is f of x plus g of x. So it's basically every single point on that purple graph is the sum of the corresponding points on the red and blue graphs. So let's say that you were evaluating an integral of f of x. And maybe let's say we were going from like 0 to 5. So remembering back to the previous video where we talked about, where does the integral come from? We were adding up all of these rectangles, right? So if you were to take a rectangle on this graph, and I'm just going to kind of draw a random one, I'm not going to worry too much about, how wide it is or anything like that. The base of your rectangle would be delta x, and the height would be f of xi. So remember, xi just represents the ith point that you're using to find a height. So I'm saying xi and not x1 or x2, x3 because I'm not trying to be specific about which rectangle. I'm just trying to say, some rectangle. And so the area of this rectangle would be f of xi times delta x, right? That's how you would find the area of this one specific rectangle. And then to find the total area, you would be adding all them up, and then you would be taking the limit towards having infinitely many rectangles. So similarly here, if we wanted to find the integral of g of x, we'd basically be adding up all of these rectangles again. And so here we would have a base of delta x and a height of g of xi. And so in this case, the area would be equal to g of xi times delta x. So now if we go to the corresponding point on the sum, well, if we were to make a rectangle there, the base would still be delta x. And now the height would be f of xi plus g of xi, right? Because that's like all of the points on this graph of f of x plus g of x are just the sum of points on the other two graphs. And so the area of this purple rectangle would be equal to f of xi plus g of xi times delta x, which is the same thing as f of xi, because of distributive property, f of xi times delta x plus g of xi times delta x. So basically, what I'm saying here is because the rectangles that would make up the area for the sum graph, that you can basically see them as the sums of the rectangles from the original two graphs. Like literally, if you took this red rectangle and stacked it on top of the blue rectangle, you would get the purple rectangle. And because that's where the integral comes from, because it comes from this idea of adding up all these rectangles, that's why the additive property kind of works the way it should, right? That you just add up two different rectangles and get the sum of those two rectangles kind of as you would hope it would work out. Okay, so let's look at an actual example of this, because that was more of just kind of a way to visualize what's going on. So let's say that we were trying to evaluate the integral from 0 to 2 of the square root of 4 minus x squared plus 2x dx. So I just want to show you what that graph looks like of this function, just to kind of show you that if we were trying to integrate square root of 4 minus x squared plus 2x, I want to show you that it's not really a shape that we would know how to find the area of. So if you look on Desmos, this is the graph of that function. Y is equal to square root of 4 minus x squared plus 2x. So if we're integrating from 0 to 2, we're looking at this part of the graph, but it's just like a funny curved shape. Like this is not something that at this moment in time we know how to actually evaluate. However, if we split this function into, or this integral into two integrals, then we'll have two integrals that we actually do know how to do. So using the property that we just described above, we can break this into the integral from 0 to 2 of the square root of 4 minus x squared, and then the integral from 0 to 2 of 2x. So why is this useful? Well, the first integral, square root of 4 minus x squared, so we talked about this a couple of videos ago, how that is a semicircle. And semicircles are something that you're going to want to be familiar with in this class. So if you have anything of the form square root of some number minus x squared, it's a semicircle. And so specifically, this is a semicircle within a radius of 2. And so it's going to look like this. And so we're looking for this area here. So what is that area? Well, we know how to find the area of a circle. It's pi r squared. And the area we're looking for is 1/4 of the circle. So that first part of the integral, this part, is going to give us pi r squared. So that's 4 pi over 4, which is equal to pi. So 1/4 of the circle gives us an area of pi. And then for the second part, well, here we want to integrate 2x. And so that's another one, because it's a linear function, it's one that we're going to be able to just use geometry to figure out. So if we have the function 2x, that's just a line with a slope of 2 going through the origin. So something like this. And we're integrating it from 0 to 2. So if you were to plug in 2 into this function to figure out the height, you would get 4, right? Because the function is, so here we have, I'll just label these. This is 4 minus x squared root of 4 minus x squared. This function here is y is equal to 2x. And so the area of this would be base times height over 2. So the base is 2. The height is 4. And so we get an area of 4. And so altogether, our total area is going to be pi plus 4. And yeah, that is our answer. So pi plus 4. So, and that is truly equal. That's the same as the area under this strange curved graph. So I think this rule is one that you can kind of just take for granted and just be like, oh, of course it works, that you kind of split things up and just add them up. But I think it's actually really interesting. Like, what we're saying here is that this area, which is a perfect quarter circle, and this area, which is a perfect right triangle, if you add those two areas together, you get the same thing as in this graph, this like strange curved region that doesn't really look like a circle or a triangle. So I think it's kind of interesting. And same thing works with subtraction as well. So one thing I just want to mention before we move on to the next rule is kind of a non-rule. So something that is not true. And this is a really common misconception, and we're definitely going to talk more about this once we get into actually evaluating integrals. But if you're taking the integral of two functions multiplied together, it is not true that you can just take the integral of each function individually and just multiply them together. It just doesn't work out that way, and I'll try to show you why not in a second. I think once we get into next week's videos, it will be even easier to kind of, I think, convince you that this rule doesn't work. But let me just quickly show you something kind of using the same reasoning that we did up here. So it is true that if we have two functions, f of x and g of x, it is true that you can make a new function, f of x times g of x, by multiplying them together. And so that's actually what this purple function is here. This is the function f of x times g of x. So if we were to make a similar rectangle to what we did in the last example, so this would be our rectangle where the width was delta x and the height was f of x times g of x, because this is the function f of x times g of x. And sorry, I guess I should say f of xi times g of xi. So in this case, the area of this rectangle is f of xi times g of xi times delta x. So that would be the height and the width. However, that is not the same thing. So if you tried to take the areas of the blue and red rectangles up here and multiply them together, in that case, you would get f of xi delta x times g of xi delta x. And that's not the same as what we have above, right? Because there's too many delta x's. So I don't think this is like the most convincing argument. I think we'll see more convincing arguments for why this multiplication rule doesn't work next week. But I just wanted to kind of show this to you, just because I think if you believe the story up here, you might be inclined to think, well, why wouldn't it also work with multiplication? And really the reason it doesn't work with multiplication is because when you're adding these two things and multiplying them with delta x, the delta x distributes in, right? And so you end up with each of them having a delta x attached. But when you're multiplying, then you only have one delta x being multiplied with both. And so it just isn't going to work to multiply the areas of the two rectangles together. You'll just have an extra factor of delta x. Okay, so now a few more properties, and let's see, I'll stay on this page. So what number were we on? That was number 4. Okay, so rule number 5, and this one actually, I think of all the rules we're talking about, this one comes up quite a bit in this class. So rule number 5 says that if you're taking the integral of a constant times a function, you can take that constant and pull it outside of the function, or outside of the integral, I should say, and then just integrate the function. So why does this one work? Well, it kind of, I don't want to go through it completely like we did on this example, but it's kind of the same idea. I mean, if you have a function and you take that function and multiply it by a number, that will just stretch all of the y values of the function. And so the rectangles you'll get are going to just have a height that is c times the height of the original rectangle. So it's just this idea of taking your whole function and stretching it, and that is just going to stretch every rectangle by that same factor. And so when you add all those rectangles up, you're going to have a result that is also multiplied by that same factor. So an example of this one could be something like this. So let's say that we are trying to evaluate the integral from 0 to 2 of 5 times the square root of 4 minus x squared. So let me show you again what the graph of this looks like. So here we have 5 times the square root of 4 minus x squared. So this is half of an ellipse. And there, you could figure out an area formula for this. It's not like it's impossible to know the area of this, but that's not really an area formula that most people know off the top of their heads, right? So how could we do this without knowing how to find the area of a quarter of an ellipse? Well, we do know how to find the integral of 4 minus x squared, because that one was just a quarter of a circle. And so what we can do is we can pull this 5 outside of the integral and then just focus on the area of the thing we do know how to find. And so we did this integral above, right? We got pi, because it was 4 pi divided by 4. And then we just multiply that by 5, and so our answer is 5 pi. So we're going to use this quite a lot, because we'll see that even when we learn these kind of simpler rules for integrating, usually having a constant being multiplied with a function just makes things a little more complicated. And so you might as well kind of take that constant aside and focus on integrating the simpler function, and then just multiply your result at the end by that number. All right, couple more properties, or let's see, maybe this is actually, I think this is the last one, but then there's one other thing that we're going to talk about as well. So this last property talks about how you can add up different integrals and with different bounds. So if you have the integral from a to b of a function f of x, and you add that to the integral from b to c of the same function. So it's really important that when you're using this rule, they have to be the same function. Otherwise, this doesn't make sense. That is going to be the same thing as the integral from a to c of f of x dx. So why does that rule make sense? Well, basically, it's just that, so let's say you have a function. And so if you're taking the integral from a to b, that's going to be this area. And if you're taking the integral from b to c, that's going to be this area. And so altogether, that's the integral from a to c. So it's basically saying that, if your endpoints of your bounds line up, then you can just kind of add the two integrals together. And it also works the other way, and this is something that we'll use towards the end of the quarter. If you have an integral from between two numbers, you can actually split it into two integrals, and sometimes that will help you avoid some complications. So I want to look at an example of kind of an application of this rule, and this is a slightly tricky example, I think. I think there's one similar to this on the homework. So let's try to, we're going to express, oh my gosh, everything is freaking out here. We're going to express the integral from -3 to 1 of x squared dx plus the integral from 1 to 4 of x squared dx minus the integral from 2 to 4 of x squared dx. We're going to express that as a single integral. So some of you may be able to kind of figure this out in your head. I'm guessing most people will want to draw this out. Personally, I look at this and I really have no idea, and honestly get a little stressed out about it until I draw a picture, because I just really can't wrap my mind around how these pieces fit together unless I draw a picture. So I'm just going to draw, I guess we know the function that we're dealing with, so I guess we could just draw that. I was just going to draw some random function, but we know it's x squared, so might as well make it look like a parabola. Okay, so here I'm just going to draw a parabola. And I'm not going to be super accurate with where I put these numbers. I'm probably not putting them quite far out enough, but that's okay. So here we have -3, here we have 1, and here, let's say we have 4. Okay, so the first part that we're looking at is the integral from -3 to 1. So I'm going to kind of color code these. So let's do that one with blue. So the integral from -3 to 1 is going to be talking about this area here. Okay, so the next part is we're going to be taking the integral from 1 to 4 and adding that to this. So that's going to be now going from here to here. Oops. That'll go a little taller. Okay, and then the last part is we want to subtract out the integral from 2 to 4. So I didn't put 2 on here yet, but let's put that on here. So 2, I know that my scale is not very accurate here, so sorry that 1, 2, and 4 don't look compared to each other the way they should, but that's okay. So let's color this one with orange. So we're subtracting out the integral from 2 to 4. And so that basically means that we want to get rid of this whole part. And we want to look at, what are we left with? So if we look at the part that we're actually left with, it's going to be the blue part plus the green part without the part that we crossed out in orange, right? So this is going to be the same as the integral from -3 to 2 of x squared dx. And that's our answer. We're not actually evaluating it. We're just, expressing it as a single integral. So basically, as long as you're talking about the same function, you can add and subtract different integrals, and as long as things kind of line up with each other, it will work out nicely. Okay, so last topic for this video is another property of integrals, but it's a little bit different. So this is going to be basically a way to come up with an upper and a lower bound for an integral. So it's kind of another way of approximating integrals. It's a rougher approximation than what we've been doing with using rectangles, but it's kind of a nice, quick way to just get a vague idea of what your integral value is going to lie between. So upper and lower bounds for integrals. And so I want to, in this case, I'm actually going to do an example first, and then we'll write down the general rule, because I think it's just a little bit, sometimes it's easier to understand something by seeing the example first. Okay, so let's say that we wanted to find an upper and lower bound for the integral from 0 to 1 of e to the negative x dx. So that's the function that is graphed here. And so how could you maybe know what this graph looks like? Well, I would hope that you know what the graph of f of x equals e to the x looks like. You know, that's definitely one of those important functions that I would expect you to be familiar with the graph. And then how does e to the negative x compare? Well, when you replace x with negative x in any function, it flips that function over the y-axis, right? It takes all of the x values and flips their sign. And so this is just a tiny snippet of the graph, but maybe just to contextualize it. So the graph of e to the x would look like this, right? Something like that. And so e to the negative x is going to be reflected over the y-axis, so it's going to look something like this. So we're looking at kind of a snippet of that green graph. Okay, so how are we going to find an upper and lower bound without actually kind of going through the process of doing rectangles and stuff? I guess I shouldn't say that because there are going to be rectangles involved, but we're not going to do like a right-hand or left-hand sum. So what we're going to do is we're going to figure out what is the very highest value that this function reaches on the interval from 0 to 1, and what is the very lowest value, and then use those to determine the largest and smallest possible value the function could be. So first question is, what is the maximum value of f of x is equal to e to the negative x on the interval from 0 to 1? So we have the graph in front of us, so we can actually just kind of look and say, oh, well, it's 1, right? Because that's the highest value this function reaches between 0 and 1. But if you didn't, then you could actually use calculus in this context, right? So if you go back to Calc 1, you know in that class you learned how to find the max and min of a function on an interval. And basically it involves seeing if there's any critical numbers. In this case, there aren't. And then just plugging in the endpoints as well as any critical numbers. And whatever's the highest value is your max, whatever's the lowest value is your min. So in this case, if you did that, you would find that there are no critical numbers. There are no places where the derivative of e to the negative x equals 0. And so you would just plug in 0 and 1 and see which one gave you a bigger result. The biggest result you'll find is by plugging in 0. So the maximum value is going to be equal to 1. So the answer here is 1. And maybe, yeah, I'll just say that, 1. So I want to draw a rectangle representing something here. So let's say that the function f of x equals e to the negative x reached a height of 1 during the entirety of the interval from 0 to 1. We know it doesn't, but because 1 is the very highest point that it reaches, we know that like the entire function lies below this blue line that I just drew, right? And so that means that if we were to take the area of this rectangle, we know that it's going to be bigger than the actual value of the integral, right? Because we know that 1 is higher than the function on most of this interval. And so the very highest that value that this integral could have would be 1. And then the next question is, what is the minimum value? Of f of x is equal to e to the negative x on the interval from 0 to 1. So again, here we can just look at the picture, but if you were using calculus, again, you would see that there are no critical numbers. You would plug in 0, you would plug in 1 and see what gave you the lowest value, and you would see that you'd get the lowest value by plugging in 1. So what do you get if you plug 1 into this function? You get, and maybe actually this is what I was thinking of writing earlier. I'm just going to go for it. I'm just going to say here. So the maximum value we got was f of 0. The lowest value we'll get is by plugging in 1. So f of 1 would be e to the negative 1, which you could also write as 1 over e. And so that tells us that because we know that the function is always greater than or equal to this height of 1 over e, that means that this green rectangle, whatever the area is of this rectangle, is going to be we know that the actual value of the integral is greater than or equal to that. So basically what's going on here is that the area of the blue rectangle and the area of the green rectangle give us these rough upper and lower bounds for the value of our integral. So here we can say that, let me kind of write this down in words first, and then I'll write something in with math symbols. So that means that the integral from 0 to 1 of e to the negative x dx must have a value that's between the values of, if you were to integrate from 0 to 1, 1 over e, right? That's the lower bound. And if you were to integrate from 0 to 1, and actually, sorry, let me make room here. Let's actually evaluate this. Well, 1 over e is a number, right? So that's just a height. So we would just do base times height. And so the base is 1, the height is 1 over e. And so that would be the lower bound is 1 over e. And then the upper bound is going to be the integral from 0 to 1 of 1. And that's just going to be a rectangle with an area of 1. So basically what we just figured out is that the integral from 0 to 1 of e to the negative x dx lies between 1 over e and 1. So that is our upper and lower bound for our integral. And just to be clear, the fact that I just don't want you to think that this and this are the same, right? And this are the same. That's just because the width of our interval was 1. So if, for example, we were doing an integral from 0 to 2, then we would have actually 2 over e and 2 here. Because where are these two numbers coming from? They're coming from base times height. And so the heights are 1 over e and 1, and then the base in this case also happens to be 1. But I don't want you to think that the max and the min value of the function are always going to be the numbers that go here and here. In this case, it's kind of, I don't want to say it's a coincidence, but it's because the base of our interval is, basically our interval has a length of 1. Okay, so let's try to summarize in general what's going on here. So in general, if a function f of x, actually let me put it in this order. So if you have two numbers, I'm going to use little m to represent the lower value and big M to represent the upper value. So basically this is just saying if your function always lies between two numbers, and when we're talking about these two numbers, we're talking about y values, right? So the little m is basically the minimum value on the interval, and big M is the highest, the maximum value on the interval. So if you have a function between these two values on this interval, then you can conclude that the integral from a to b of f of x dx is going to be between, so the lower possibility will be m times b minus a. And then the upper possibility will be capital M times b minus a. So where is this coming from? It's just basically what we just saw in this example. So if your function f of x is something like this, well, the minimum value in this case would be here, right? And sorry, let me put in some bounds. Actually, I'm going to make it like this. Let's say a is here and b is here. So it looks like the minimum value on this function is here. This is little m. And so this is saying that if you were to draw a rectangle with this area, the area of that rectangle would be b minus a times m, right? This is something we talked about in the beginning of the video. And then if you look at the upper bound, so that looks like the highest value this function reaches is big M. If you were to take the rectangle that has that as its height and b minus a as its width, that will give you an upper bound for the value of the integral. All right, so that is it for this video. Like I said, in the next video next week, we're going to be getting into actually evaluating integrals. So not using, geometry, not using rectangles and approximation, actually learning how we can use calculus to find these types of areas.